you.
And did you start recording, Nuria?
Yes, I think so.
I see a red dot in my small screen.
Okay, that's great.
Okay, thank you. As explained, my name is Joost Wesseling. I work with the National Institute for Public Health and the Environment in the Netherlands. There we've been working with low-cost sensors for about 6 years now. So I'll try to explain a few of the basics, but I will also discuss that you need more than just a sensor. You need a whole sensor kit. And I give a few examples of work that we do with both the SDS and the SPS, which are probably the most popular sensors for PM. So a few words on sensors, the two types, and then also I'll discuss shortly that you need something of a sensor data portal. The most interesting two films which I made, if there's time left, showing the use of sensors in incidents. If you look at sensors, well, over the last, say, 5-6 years, quite good low-cost sensors have become available. Low-cost, in my terminology, that means less than, say, 25 euros, no more than 50 euros. Professional people usually think 1,000 euros is low-cost, but we put the bar at somewhere around 25 to 50 euros. About 6 years ago, you had the Shinjai sensor, then later became the SDS sensor, the Sensirion. And if you look at gases, well used, often used sensor for nitrogen dioxide is the Alpha Sense, which is very popular at the moment. So they have become popular over the last years, but we all have to keep in mind that, of course, these sensors, we call them PM sensors, but they don't really measure the mass of the particulate matter. They just count particles in one of several ways. And that means that they have a number of drawbacks. One of them, the biggest one, being that many particle counters are very sensitive to relative humidity. Essentially, they count water droplets as if it's particles. So you need some kind of calibration. That is also already clear from the Mentimeter. If you look at shortly at, for instance, nitrogen dioxide, then there are whole other types of problems. It's much more expensive. They are cross-sensitive. So there are many more issues when looking at citizen science for gases than there are for PM. But all the sensors here shown here on the left have in common that they are very robust. They are easy to interface with a small microcomputer. And they are also quite easy to communicate the data obtained with a sensor like this using either Wi-Fi, LoRa, or whatever your favorite communication protocol. Like I said, you need more than just a sensor. So suppose that you have a sensor, either a PM sensor or a gas sensor, that doesn't really make a difference. You need something of a microcomputer to average the data, to decide when to send data, to make sure that the sensor is working properly. So popular microcomputers are the Arduino or the ESP8266, which comes with the advantage that it also has a Wi-Fi board on the chip. But you need at least one of these to control your measurements. Many sensors are sensitive to either temperature or relative humidity. So most sensor kits have also a sensor for these two. Some sensors also take other things into account, but you need at least temperature and humidity. Then, of course, you have data, but now you want to send it somewhere. So you have to decide, am I going to send it using Wi-Fi, 2G, LoRa, or the more fancy popular ones, narrowband IoT or LTE-M, which are essentially old variations of the old 2G network. But you have to decide, and you have to make sure that your sensor kit also contains hardware to perform this communication. And of course, most people forget you need some kind of housing. There are a number of popular housings. For instance, the two elbows are popular with Luftdaten, now known as Sensor.community. But you can also use a weather house or something that you print yourself, or just an electronic box where you put the sensor inside. Doesn't really matter as long as it keeps the moisture out and the air in. And then, of course, once you have data, you need to send it to a server, because one sensor providing only data from that sensor doesn't really give reliable results. So you have to have a location where you can look at the data, where you can process the data, where you can combine all the data. So you need some kind of server where you can send your data. This is an example of a sensor kit that we are presently using at our institute. So all the things I mentioned, the microcomputer, we use narrowband IoT, so we have an electronics board. We also use the nitrogen dioxide here, the SPS, both the SDS, and it's in a box. It's about a small shoe box for, say, children's shoes. But it's closed, so we have an inlet on the side here, and we have an outlet. So we need a fan to make sure that there's a constant airflow through the box. So we also included a flow sensor to check on the flow. And then, of course, you need something to make sure that you have the proper power supply. So there are all kinds of issues you have to take into account before you really have any data. Once you have a sensor kit and you start sending data, we already heard about several networks during the Mentimeter questions. Purple Air is a big network. It's very popular in the US and in other parts of the country, especially on the West Coast. It has a very good coverage. Luftdaten is more popular in Europe, where especially in Germany, Switzerland, Belgium, the Netherlands, and Romania is also very popular. They have, I think, in total something like 10,000 sensors where they show the data. And in the Netherlands, we have created our own data portal because we don't only want to combine data from all kinds of citizen science experiments, but we also include data from our own experiments. So we combine all the data in the Netherlands in one view. And once you have a server where all the data is collected, then you can do interesting things like combine sensor data with models, combine them with other types of information using data assimilation or data fusion. So you can really add information, or you can add value to the information provided by the sensors. We look at these two PM sensors individually. They cost about 25 euros for the SDS, 45 for the SPS. You can find them cheaper on AliExpress, but experience learns that sometimes then when they are delivered, you have to pay custom fines because the Chinese forget to pay custom. So 25 euros is a reasonable price in the Netherlands. If we look at the SDS, it has been become very popular in stationary sensor kits. Presently, there are some 1,500 sensor kits in the Netherlands which are equipped with the SDS011. It's really cheap compared to other things. It's robust, it's very easy to interface. And the big advantage is it reports PM2.5 and PM10. Big drawback of the SDS is that it's really sensitive to ambient humidity. So to correct for that on during humid hours, you really need some kind of substantial calibration. The sensor itself really has to be calibrated for that. On the other hand, the SPS30, it's a bit more expensive, about almost twice as expensive. Has become popular over the last, say, 1 or 2 years. It's similar to the SDS in the way you can use it. It's also robust, easy to interface. Software is available all over the internet. And big advantage, it's much less sensitive to ambient humidity than the SDS or any other PM sensor that we know of. So it's a very, very nice sensor to use. Biggest drawback for citizen scientists may be the price, because if you want to do it cheap, then a factor of 2 does make a difference. And for us, the biggest drawback is that it does not report PM10 data. Or at least it reports data, but the PM10 output of the sensor is just the PM2.5. And sometimes maybe 1 or 2 micrograms on top, but there is no serious PM10 data reported by this sensor. That was observed by us and also by many others. And as I said, it's much less sensitive to ambient humidity, but it still needs some calibration if you want to get the best out of the sensor, but not as much as, for instance, the SDS. Both sensors use essentially the same kind of configuration. You have an airflow, which is driven by a fan that's available in both sensors. And you have a laser somewhere within the housing, and it shines through the airflow. And then, of course, if there are many particles in the air, then the laser will reflect off that. So essentially the electronics in the sensor translates small effects observed in the light beam into PM concentrations. But the problem is the light reflected of matter, or is it reflected of water, or even something else? And the particles, are they very heavy particles, so with a large density, or light particles with a... You don't know that. So all these sensors work with assumed average densities for the particles to translate numbers of particles into mass. That's a drawback, but it's not really a big drawback, as I'll show. The effect of humidity on the SDS is shown in this figure. We did many experiments co-locating the SDS with official measurements. And if you then compare the ratio of the SDS and official data as a function of the relative humidity, then at very low humidities, it has a tendency to underestimate the official measurements. But at higher humidities, say above 95%, then you see that there can be very large ratios between what the sensor is reporting and the official measurement. So you can have situations on cold, humid mornings where all of the country, all the SDSs report 500 micrograms of PM, whereas in effect it's only 10 micrograms. It's just the moisture that you see. So you have to take care of that in some kind of calibration. We have developed a calibration mechanism for that, and the results are shown here for an example. These were data for about a year and a half ago. You see the blue curve, which are the PM concentration, PM2.5, reported by an SDS sensor. And the red curve is the result of a not too far away official measurement. And you see that the sensor has a tendency to substantially overestimate the official measurements during these hours. And in other periods, the sensor agrees very nicely with all the other observations. And then you do a calibration using a network mechanism we developed. And then you end up with the purple curve, which follows the ambient official concentrations quite nicely. So if you put in the effort, and then you can get a very nice result also with the SDS. How we did it was quite simple. At first, we of course tried to calibrate each sensor individually, but then you need the local temperature and humidity, and these sensors quickly break down. We don't know of any cheap temperature humidity sensor that lasts for on average longer than a few months. And also using historical moisture correction didn't really work. So the idea was quite simple. Look at all the locations where we have official measurements, indicated here by the red circles, and just look at the average values of all the sensors which are close to this official location. In some locations we have many sensors, many official locations. In other parts of the country it's not that nice. But then you can get some kind of average calibration at each location of a circle. So we have a whole set of local correction factors in the Netherlands for every hour, and then you can make an interpolation of these correction factors, which ends up with a kind of correction field, which you can then apply. If you do that, and then of course it's good to know how good this procedure works. But first, another picture that I had forgotten about. If you have, this is an example what you can do with these calibrated data. This is for an hour a few months ago, where the dots, the squares indicate official measurements, PM2.5 measurements. And we also calculate a map for PM2.5 concentrations in the country for every hour of the day. And this is the official data set and also the official background map for the Netherlands. If you now add all the information we get from the sensors, and these are then the calibrated sensors, so you see in parts of the countries, the sensors are clearly indicating higher concentration. So if you then use the information from the sensors and combine it with the existing official map, you can slightly adjust the official map to give a better description of both the official data and the sensor data after the calibration. It's a procedure called data fusion, where essentially you take all the information that you have and try to get the most out of that. So by doing this for every hour of the day, you have official data, you have the official map, but you also have the sensor data, and you have an optimized map after the data fusion program. So that's additional value that you can get out of all the sensor data. But of course, you need a lot of sensors to do this. One sensor or two sensors doesn't really help to do this trick. You really need hundreds or 1,000 sensors to do this. An interesting question is how good or how bad is this whole procedure working? We did a test over the year 2020 where we compared sensors to close by or co-located official measurements. And this is part of the data set that we have for PM2.5. We had some, I think, 60 of these sensor official location combinations. So on the horizontal axis is the official data, PM2.5, and vertical is showing data from all different sensors. And in many cases, there's a reasonable agreement, or quite good agreement, between the calibrated sensor and the official measurement. I must say the official measurement was not used in the calibration. So we are comparing a sensor with official data that was not used to calibrate the sensor, to keep it fair. In some cases, there's a really nice correlation between the sensor and the official measurement. And I must say we use both Belgian and Dutch data for this. And in some cases here in the middle of the picture, there's one sensor which doesn't really do anything. It just creates some kind of noise independent of the ambient concentration. Sometimes also the procedure doesn't work as nice as we would like it to be. These are two on the left part of the figure. There are two examples of sensors which still keep on overestimating the real concentrations. So our calibration mechanism still needs to be worked on for this part of the country. And then also on the right bottom part, there's a sensor which sometimes works nicely, sometimes it does completely different things. So, but that's inherent in using these type of sensors. But overall, these data are quite nice. So you can really use the information coming from these sensors. That's as far as the SDS is concerned. I want to discuss a project we are doing, or we were involved in, using the SPS sensor. It's a bit smaller than the SDS. It takes a bit less power. So an experiment in the Netherlands was to equip about 550 bikes with portable sensor kits. So shown here on the top left is a sensor kit connected to the bike, and they can operate about 8 hours on a battery. And they are equipped each with the SPS sensor, a GPS, and they also have a narrowband IoT communication chip. They provide 10-second average data during all the time that someone is on the move with the bike. And in the province of Utrecht, which is roughly within this red square, we have 4 of these kits co-located with official measurements to also get a feeling for the calibration. You see that this is a picture of a few days ago. There are still people biking around with the sensor kit, so the project is still running, but we have looked at the data for the past year, so 2020. Shown here are the results of the co-located SPS30 sensors with official measurements. And these are raw data, no calibration whatsoever. It's just what's coming out of the sensor. And compared to many, and this is data for the full year 2020. So you see that there's really a very nice agreement between the sensor and the official measurements without any calibration whatsoever. The main issue of the SPS is that, especially at the lower concentrations, and these happen a lot, so you can't really see it in the figure, but at the lowest concentrations, the SPS has a tendency to underestimate, to really seriously underestimate the real concentration. So we have a mechanism to correct for that. So you end up with the correct yearly average value. But apart from that, especially at the higher concentrations, the sensor is performing very nice. One of the things we did was to take the sensor data for every individual bike trip and then estimate the local background concentration during the bike trip, because most people in the Netherlands don't bike that far. A bike trip takes about 15 minutes and a few kilometers. So you can try to define a local background concentration and then look at how much the concentration is varying along the bike trip. And if you do that for all the data, and we had some 70,000 valid bike trips in 2020, you can estimate the exposure to concentrations due to traffic on the street. And then you get a figure like this. So red is more than, say, roughly 3 micrograms exposure, and blue means less than, say, 1.5 micrograms. This is the city of Utrecht, and you see that in the center of the city, the exposure, the contributions from traffic are highest. This is not very surprising because the city of Utrecht is small streets, relatively high buildings compared to the width of the streets, many bikes, many buses, many lorries, many taxis. So we're not surprised to see higher concentration contributions here. And also on a number of known routes where there's a lot of traffic, you see higher concentration contributions. And in other parts of the city where not really much is happening, we find lower concentrations. It's all on average, because there are also, for instance, here, there are a number of trips taken regularly by a few people, which show higher concentrations, and we have no reason why that is. So maybe that's still a faulty sensor. So you have to take that, the uncertainty of sensors into account when looking at these pictures. But overall, the view is quite nice. And we see this in all the cities and towns in the province of Utrecht. City center are the highest concentrations, busy roads are the highest contributions. And if you go to the smaller roads or situations where there's a lot of distance between traffic and bicycles, then you see that the exposure to traffic emissions is also quite low. One of the things we did to get the most out of the data ourselves, like I said, we created a Dutch sensor data portal because we wanted to have an easy access to all our data, but also data from everyone else. It's also open to the public, so everyone can use it, everyone can download all the data. Most of the data portal is air quality, but we're also working on water quality and noise. And most of the sensors shown here are SDS011. I think they're now about 100 SPS, and there are about 1,400, 1,500 SDS. And everyone with a sensor can send the data to the portal. And we also have an agreement with the people from sensor.community that all their data is also shown on our portal and also can also be used. And if you have a sensor like the SDS or a plant tower, which is similarly susceptible to relative humidity, then it can be calibrated automatically. The only requirement we have is that all data must be open and transparent. Given all the data, we also create these data fusion maps for every hour of the day. So and essentially, you can see that most of the sensor data, which seems to fluctuate, has a tendency to fluctuate a bit, it's kind of averaged once you use the data to get better air quality maps. So it's a way to get a more stable view of the information. If you want to have more information about individual sensors, then you can click on each of these dots. And these are two sensors. One is an SPS and one is an SDS, and they are located within 2 meters from each other in my own garden. So we can nicely compare the results. And the bottom one is the SDS, and the purple curve that you show here, which is slightly underestimating the data, that is the raw data from the sensor. And the blue curve here is the calibrated data of the sensor. And essentially, the blue curve follows the data quite nicely. And the orange and red, the curves are from a traffic station, some in the city of Utrecht, and a rural background station about 20 kilometers to the east. So they're not really close by. But the fact that the sensor follows the main patterns of these two locations shows that we're mainly looking at large-scale fluctuations of the PM concentrations. There's one small period here where we see a number of peaks shown by the sensors. 2 of them are also shown in the official network, but a few not. So they probably are due to relative humidity. That's even more clear if we look at the SPS without any calibration whatsoever. Here we see that, again, it has a tendency to slightly underestimate the data provided at the other locations, but it follows the general pattern very nicely, like the SDS do. These peaks and these peaks are followed well, to a high degree. And where the SDS shows a number of peaks that we don't understand here, they are not visible in the SPS data. So probably these peaks of the SDS are really caused by humidity and have no real physical meaning. So by combining information from the SPS and the SDS, you can get interesting combinations. So that's why we now use sensor kits where both the SPS is present, because it gives a good PM2.5 value, but also the SDS because it's sensitive to humidity, but it also gives an estimate of the PM10, which the SPS does not. So by combining those two sensors, you can get the better information. I'm not sure how I am in time, but if there's, unless Nuria or Hester say I have to stop, I have two examples I want to show, because most of the use of sensors is as if they are official measurements. So you put them somewhere, you wait a long time, and then you look at the overall results. But during incidents, they also have a very nice purpose. This is a map we created during Easter of 2019. Due to a drought, there were no Easter fires in the Netherlands. They were all forbidden. But in Germany, all the Easter fires, and they are very popular in Germany, were allowed to go on. And the wind was coming from the east during this weekend. So when we then look at a map created from all the sensor data, then we see these high concentrations coming in from Germany, and look at the scale, it's 130 micrograms, the red wave. So we see very high concentrations coming in from the east. Then there's a drop in concentrations because they all go to sleep. But then again, the next day they all start putting on the fires again. So we see how, again, there's a whole wave of air with higher concentrations is entering the Netherlands and moving from east to west. So you can create animations like this with official data only, but having so much more sensors makes that you get much more detail in this figure. Another example is a fire that took place about almost a year ago. There was a location where a lot of car tires were stored, and there was a big fire there, and well, car tires create a lot of smoke. And it was, well, you can see here, it was really visible over a long distance, but we had the big advantage that there was a very stable southeasterly wind, which didn't vary much over the day. So when we looked at the sensor data, and we were lucky that there were a lot of sensors. So this is where the fire started. So already quite quickly you see this plume of higher concentrations move over the country. Well, probably here the fire has been put out, but here we still have higher concentrations all over Amsterdam. And this is about 100 kilometers, and there's the red means 40 micrograms. So we had a day with very low ambient background concentrations for PM, and so you could really track this huge cloud also in all the sensor measurements. That's what I wanted to present. So if there are any questions, I'm happy to answer them.
Thank you, Joost. I think it has been a very, very interesting presentation, and yes, there's a lot of movement in the chat. So let me see. You have many questions for you. I think one of the questions was related to the calibration, on-site calibration. Is there anything? What technique are you using for calibrating sensors that are not collocated? You were mentioning a little bit about that. Can you maybe say a little bit more?
Yes, we have about 30 official PM2.5 measurements in the Netherlands, and about 40 PM10 measurements. So at all those locations, if there's data available, we look at the ratios of the official measurements and then the surrounding sensor data. And that gives us a local correction value at that location. So on a good hour, we have maybe 40 locations with the correction factor, and then we perform an interpolation over the whole country. to get a correction factor or a calibration factor for any location in the country, which we then apply to all the sensors there.
It's nice. I see Lucas was commenting that in the Netherlands you have almost 2,400 sensors from sensor community there. So that's will allow you to do this nice interpolation. Let me see. Julieta is asking if this calibration that you are commenting is available to read somewhere, if you have already some publication, or can she find it?
We have written a very short description in an article we wrote about 2 years ago. I can ask Hester to distribute the reference of that later.
Perfect. Marita is also commenting about the SPS30 that in the figure you were showing, it has like a curve or band in the inlet, and that might prevent the sensor to correctly capture PM10. So I also like from some of our work, we could also see that, and also is published in the literature, that these sensors fail to correctly measure PM10. So do you offer data of PM10 in the portal, or you focus only on PM2.5?
No, we provide data both for PM2.5 and PM10. Because if you know how much of the concentration you are missing, you can correct for it. So you can make a valid calibration for that. But it's true that most particle counters are much better for PM2.5 than they are for PM10. So the calibration factor has to be more dominant for PM10. But then again, if you do the calibration and compare the results to official measurements that you did not use in the calibration, you still end up with very decent results.
Yeah, but this probably just me saying a comment on that. But what if the source is not related? Like, for example, I don't know, like wood burning, it will be mostly PM2.5, but or road dust. Like maybe if there is not such a good ratio between PM2.5 and PM10, did you work on that, or do you have any comments on that?
Yeah, the calibration mechanism is such that we don't force individual sensors to a particular value. We look at groups of sensors, and we don't change the ratios of measurements within that group. And we also know that most of the calibration is due to high humidity, and that's usually high or low for 10 square kilometers or more. So even if you have a sensor measuring wood burning in one street and not wood burning 2 streets further down, then they will both have the same problem with the relative humidity. So you can still correct for it, but it's true that if there are very different causes for the high concentrations reported by the SDS, then you have to be careful about interpreting the results. So we're not in any way saying that you can get official results out of the SDS, but we do say that you can correct for the effect to some extent. So you get a reasonable result instead of complete garbage. Because the alternative is having 500 micrograms, and after the calibration, maybe there's still an uncertainty of a factor of 2, but then it will be 20 compared to 10 micrograms instead of 500 compared to 10 micrograms. So you have to take it into perspective that these calibrations, they are large in situations where the sensor without calibration is producing complete nonsense.
Yeah, and also following that questions, Franz Fierens has a question. Will the calibration method use not eliminate almost completely the impact of very local sources, like for example, wood burning? No,
because we don't change the ratio of the measurements within such a group of sensors. So if there's one sensor with a very high relative concentration within such a group, it will stay a very high relative concentration. And furthermore, if there are enough sensors in such a group, then we don't use the highest values and the lowest values. So the sensor showing a lot of wood burning concentration will keep on doing that. We take precautions to make sure that we don't average out everything. All the relative relations between the sensors in an area are the same before and after the calibration.
Thank you. And then moving a little bit, some questions also to the sensors mounted on bikes. There was a question here from Guillermo Villena. Is there any influence of the movement of bicycles in the measurements?
We don't think so. We looked at the variations between official measurements and co-located sensors. We looked at the variance between different sensors co-located. And we also looked at values measured by bikes while they are on the move and coincidentally meet each other. So we have divided the whole region of the province of Utrecht into a grid of each grid cell 25 by 25 meter. And we can detect once or if two bikes meet in such a cell. And then, of course, they should measure roughly the same concentration. And it's only a very small bit larger than if you look at the variance of a single stationary sensor. So we think that's not too big of an influence. And of course, we also thought about it. We were involved in the design. So the inlet is on the bottom of the sensor and it's perpendicular to the airflow. So there shouldn't be too much of an influence, and we don't see much of an influence in tests.
Nice. There is also a question from Raquel Gomez asking, why do you choose these two sensors? Did you look at any other, such as the purple air sensor, or is one of the one found in purple air sensor?
Well, purple air became popular at least in the Netherlands only quite recently, and I think there may be 10, 15 or so purple air sensor kits in the Netherlands, so it's not very common here. We ended up using the SDS a few years ago and did a lot of experiments with it. And for instance, the plant towers are technically roughly comparable to the SDS, so they have the same problems, they have the same benefits. So we thought, well, let's just stick to the SDS because it's so popular. We also quite soon started using the sensor.community data, which are all SDS data. So we decided to focus on one sensor to really try and understand that sensor. But then when the SPS became available and it has some real benefits for the PM2.5, we decided to also use that sensor. But that doesn't mean that all the other sensors are worse, or maybe if there's a better sensor where my telephone is starting to make noise. Don't know why. But if there's once a better sensor shows up, we'll gladly start using it. And quite a lot of the other sensors are quite comparable to the SDS. So that we don't use them doesn't mean that they are bad.
Yes, and maybe then I can just open, like if any of the participants have questions, you can just turn on your microphone and ask directly to Joost. Maybe I didn't read your question. Just please go ahead.
There was a question about costs, like the general cost of all these sensors together, I guess. Not only for the unit you have, the fixed unit, but also the bike unit.
Yeah, the fixed unit I showed you with the shoebox with all the sensors included, that will set you back about 700 euros. And then you still need to calibrate it, which is going to cost a few hundred euros. But I must say we have a tendency also for the electronics to use the more high quality components. So we don't use AliExpress. You can buy an Arduino for 25 euros in the Netherlands officially, or for 3 euros at AliExpress. So we buy the expensive, we buy all the expensive stuff because as an official instance we can, but it's really worthwhile. The bike units will cost about, it depends a bit, they've had several types, in the order of say 250 euros. And the largest individual price is caused by the narrowband IoT component, which costs about 100 euros. But if you want to send data from anywhere in the country without having any communication issues, then narrowband IoT is the best way to go.
I guess to add to that, Lucas is commenting that a sensor.community sensor kit costs you less than 50 euros. So that is a really inexpensive way. And we are also using a sensor kit for schools, and that costs you around 125 euros. So you can find them in the price range of a little below 50 euros up to several hundreds.
Yeah, you have to take into consideration which sensors you use. The 700 euro, then you have also the NO2 sensor, which is including the electronics, is also 150 euros. Sensor itself is 60 euros, the electronics 90 euros. So it quickly adds up once you want to have all the information in one kit.
Yep.
Yeah, I think we take this last question, like it was asking like if also like those cheap sensors include the temperature and the relative humidity, or you need to have a separate sensor?
Well, most kits and also the design of sensor.community, there's a temperature humidity sensor included. But as I said, they break down really often. And even worse, quite often they show strange values. And if you don't detect that, then you start correcting for the humidity effect using the wrong humidity reported by your temperature humidity sensor. So that's why we don't use local humidity measurements. We use an interpolation of the whole Meteor network available in the Netherlands. It has a drawback that you don't know the exact location, but it has the big advantage that you can really rely on having decent values.
Yes, thank you so much, Joost. I think questions keep coming, but we have only 4 minutes left to the meeting. So, and I think Hester, you wanted to ask also something to our participants. Is that true, or is that correct?
I had prepared some more Mentimeter, but maybe because we have very little time left, and I thought the discussion was very good. We would just like to invite you, or maybe I can start the Mentimeter and just show you one slide, and then you can. We would like to ask you what other subjects you would.
Yeah, I got
like
you.
to
Share the link, and I can say like we want to get from you a little bit of input on what can be our next talks about, and it actually doesn't mean that we need to finish the talk about the data quality and the challenges of using sensors with this talk. I see there is many questions, and so we can have more talks also about that. But we want to listen to you. What would you like to listen about? What would you like to discuss in our next working group meeting?
Or if you want to volunteer to give a lecture, of course, that is also very welcome. So if you think I have a nice presentation and I would like to have an international community looking at it, or you want to discuss something, that would also be great.
Yes. Yes, it can also be like a challenge you are facing, like how to keep citizens engaged in your project, you know, like it does not necessarily to be a success story. It can also be just something you want to share and get inputs from the rest of the community. And with this, I probably stop recording.
Okay, see some beautiful